Hello friends, I'm a cloud solutions architect at Microsoft and my aim is to empower every single person to be better at technical interviews. Keeping with that goal in mind, today we are going to do an awesome lead code problem, so let's get started. So the problem we are going to solve today is called copy list with random pointer, and if we see some of the popular companies who have already asked this question, there are companies like Amazon, Facebook, Bloomberg, Microsoft, Apple, Adobe, Google, ByteDance, eBay and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem and a very well-liked problem. Basically, in this problem, we are being asked to copy a linked list. The thing is, this linked list is actually kind of a tricky linked list. It's not your common linked list. So if we know by a definition, the linked list that we understand has a structure that looks like this. And the last pointer points to a null value. So this is a typical structure of a normal linked list. But the linked list that we are given in this case is actually kind of little bit of tricky. It is a linked list that looks like a structure that is something like this. Where in this structure, we have these two parts common. So the green values over here are defined as the regular linked list pointers, where we have a value and we also have a pointer that refers to the next item inside the linked list. The thing is, at times we are also given these random pointers in our linked list as well, and the purpose of these random pointers is that they can point to anywhere, and basically we need to keep track of all of this, and on whatever the given linked list that we have been provided, we need to create a deep copy of that particular linked list. So this is what is being asked in this problem. Like, if you cannot find, or if you try to understand, you can read this problem statement again by pausing the video right now, or you can see some examples that I have shown over here. So let's take a look at the first example. As I was mentioning, that this is not your typical common linked list. You see, in this linked list, we are given one value for every single item. But thing is, with this value, rather than having just a single pointer that points to the next element, which is defined over here as this next pointer, we are at times also given this random pointer as well that can point to any direction, and we need to keep track of that, and we need to create an exact copy. So inside the input, we are only given the head of the linked list, and this is the original linked list structure behind the scenes. And in the output, based on this given head value, we need to iterate over this entire linked list, and after iterating, we need to create an exact copy of it. So if we see some structure of this given linked list, it is going to look somewhat like this. So in the output, basically we need to we are initially located at this position. This is the head of the linked list, and we need to find a way to iterate over this entire linked list in the exact manner and create a deep copy. So what does creating a deep copy means? Means that if some node does not exist in our copy, then we would create a new node, take all of these values exactly as mentioned, and put these values inside our new node and mark it as the node in our sequence, and then in the end we need to return the newly created linked list. So basically we are going to create like 5 different nodes. Every single node is going to look pretty much similar to this, and they are all going to have a structure that is common over here, and basically we are going to return this as the answer. So this is the whole ask. There are few other examples given as well, but they are not as important. They are just kind of simple. So I think you get a general gist of what are the things are being expected. Now we have already done similar questions like this, and even say for an example, if this was just a random linked list, it would have been too easy for us to solve this problem, because what we could have done is we initially start with the first position, so with this head position, and just keep on creating a new linked list based on whatever the values we are iterating over right now, because we have a very certain path in any linked list where the first node is the value, so we can just copy whatever the value this has. So say for an example, this has value number 5, we can just copy this value as value number 5, and this has value number 6, we can also copy value number 6, and if this has value number 10, we can also copy value number 10. So these things are easy to do. It is also easy to iterate to the next node inside the linked list because we are directly given the pointer, and using that we are also going to do the same thing. And basically in the end, when we reach to the null value, we have reached to the end, and simply we can return this as the answer. Now copying is not as simple in this case because we are dealing with a structure that looks like this, where there could be potential possibility of cycle. What do I mean by potential possibility of cycle? Say for example, we are given these two nodes, the values are 7 and 8, and we know for sure that this node is going to point over here and this node is going to point to the null value. These two things are fact, but it could be possible that these two random nodes, so this random node points over here and this random node points over here. Now if we try to iterate over this, like a different version of this linked list, what is going to happen is that, okay, currently we are located at this head value. So what would happen in these cases? Well, the thing that would happen in these cases is that over here, rather than coming back to this point, we might end up creating a whole new node with the same value 7, and we will try to iterate over this value. And this over here again, for this particular 7, the value is pointing towards 8, so we might create a new node 8, and then we keep on repeating. So basically, because there exists a cycle over here, it is possible for us that while creating the copy, we could end up in an infinite loop, and that could be disastrous. So we will have to avoid that in any single cost. Okay, so say for an example, this is one of the input that we are given, and we are trying to convert this and trying to create a deep copy of this. Basically, we are given this as the head node, right? And now we need to iterate over this one. Now, but the thing is, in this case, if you see, there is the cycle present amongst these random nodes. So this is a cycle, and if we don't take care of it, we will actually keep on ending it in an infinite loop. Now the thing is, in order to detect any cycles, we actually have a great way of doing it in all the graph problems, right? But the thing is, you would say that why am I mentioning graph over here? Because clearly this has been shown as a list or a linked list kind of a problem. The idea is that rather than treating this as the linked list problem, we can actually treat this as a graph problem, where every single items can be treated as the form of vertices and edges. Because remember, in the graph, the two most important items are vertices and edges. So for the vertices, we can actually consider these input nodes of the linked list as the vertices, and for the edges, we can actually consider these like next edges, so the white edges and also these purple edges, to be considered as the edges. Now in this case, the edges are going to be directed and also unweighted. Now after doing this, after treating this and trying to consider this as graph, things becomes much easier for us to keep track. Why? So I have actually drawn this figure where I am visualizing this given input as a graph. Now in this case, if we treat this as a graph, it becomes very easy for us to copy and maintain. Why? Because the logic we can use in this case is that any single node, we can actually create a visited directory or a hash set or a hash table where we keep track of all the nodes that we have visited so far. So that way it is going to be great for us to keep track of everything. And once we are done with all the nodes, we can simply return the copied nodes. So the logic we are going to use is, okay, let me make this a little bit smaller. Okay, so now let's try to iterate over this given node, and we will start iterating through its head. So this is the head pointer, and every single time we are going to keep the same logic that we use in any single graph problem. That first we will check that whether that particular node has been visited or not. If it has been visited, we will skip it. If it has not been visited, we will add an entry over here and we will create its clone node, and we will keep on repeating the same process. Now for every single node, we have its edges. So basically we are going to go in depth first search manner, and in depth first search manner, we are going to go over all the neighbors of any single node and keep on repeating the same process. And also because we are repeatedly doing the same thing, we are actually going to do this recursively. There is also an iterative way to doing it, but the thing is, I like recursion better, so I'm just going to show you the recursive way. But remember, there is also an iterative way. And if we see this diagram, basically there are just few functionalities. So these white edges, they refer to the values of the next pointer, and also these purple edges, they refer to the values of the random pointer. and let's start iterating. So first we are at this head pointer, so we are at this node number 7 is not present inside our visited hash set. So first we will add an entry 7 over here, and now let's just create a new node called 7. So we will create a new node. Okay, 7 has been created. Now what is the next node of the new node? This is the random pointer. So where the random pointer is pointing towards, it is pointing towards null value. So if it is pointing towards the null value, we do not need to add it to our visited set, because remember, null is not a new node, but it's just like the end of the list. So we'll just keep track of it. So okay, this one is like the null. And also if we see in this case, the next pointer we need to go over is the next edge. So next edge is pointing towards value number 15. So we will check that whether 15 has been visited or not. 15 has not been visited, so we will add entry 15 over here. Now we will start visiting the 15's first edge, which is the random pointer. So if we go depth first search recursively, okay, so this 15th random, so let me just create a new node 15 over here, and this 15th random edge is taking towards node number 10. So 10 has not been visited. We will add an entry 10 over here, and we will also create a new node for 10. And in this case, the 10th next node, or the node in sequence, is the random pointer. So random pointer is pointing towards 13. So 13 has not been visited, so we will go over 13 node. So we will create a new entry called 13 over here in this case. Awesome. So now we have all 4 of our nodes set up, and we have also iterated towards the random pointers. So now at 13, when we iterate over the random pointer of 13, it takes us back to the node number 15. And because this is taking us back to the node number 15, which means we will check that, okay, whether this has been visited or not. Yes, 15 has already been visited, which means we are in a cycle. So we need to break out from there. So basically we do not care, and we will not get ourselves involved in this one, because we have already created a copy of 15. So because we have created a copy of 15 in this case, so rather than creating a new node for this particular random node, we will simply point it towards this 15 that we had already created. And that is how everything is going to work. And then we basically have taken care of this cycle without getting secluded in the infinite loop, because we use the visited hash set. And then for every single node, there is still the next node remaining that we need to traverse over, which is simple to do, because for next node it is only pointing towards the next node. And in this case, from 15, after completing this sequence, when we go to the next node, okay, this one is pointing towards value number 13. We already created a new node, so we do not need to create anything. We simply need to add the entry over here to point it towards the correct direction. Same way 13, next node is going to be 10. That is also good. And in the end, this 10 is going to point towards the null value. And this is how our traversal is going to be completed. And we would have created an exact deep copy of this particular linked list with random pointers without doing any extra work. And this is like a wonderful approach. So all we did is we treated linked list as graph. And this is a great way to understand that how can two different data structures can be interchanged, and we can use trick of the one data structure in the other data structure. So I know this was a little bit complicated to understand, but if you just like try to put some thought behind it, things would make much more sense. And if we see time and space complexity in this case, the time complexity is actually going to be big O of V plus E. So V plus A is the number of vertices plus edges. Why? Because this is a graph problem, so this is what we have to deal with. And in general, in this case, rather than treating it as V plus E, we can actually treat it as big O of N, where N is the number of nodes given in the input. And in terms of space complexity, in order to use the recursion, we will have to use big O of N space. So this is a decently good time and space complexity. Well, I just need to make a quick remark. If we use the iterative approach, the space complexity would become big O of 1 in that case. First of all, we are going to create our visited hash map, and inside our hash map, we are actually going to do things a little bit trickily. So as its key, we are going to keep the values of the old node, and as its subsequent value, we are going to keep the newly generated copy that we have created. So at any given moment we encounter any already visited node, we can simply return its copy rather than creating a new node every single time. So this copy random list method is also going to be our recursive method. So first we will create a terminating edge case that if the given head is equal to null, we can simply return null. If that is not the case, first we will check that whether the current head value we are at, has it already been added to our visited node. And if it has been visited, we are simply going to return the subsequent reference value that we have stored inside our visited node hash map. If, say for an example, this has not been visited, so in that case we will have to create a new node. Now as a new node, we are assigning it to the value of the current head value that we have received as an input, and as its random pointer and next pointer, current values are null, but we are going to populate these. Now once this has been done, since this is a new node, this needs to be put inside our inside our hash map. Now notice in this case, the head is the existing node that we are taking as an input, and this node is the new node that we have created, which means we are storing the copy as the value inside our visited node hash map, and as a key we are using the older value. So now for this particular node, we have taken care of the value of that particular node. But the thing is, we haven't taken care of the next pointer and also the random pointer. So we will do that. In order to do that, we will actually have to call for the next pointer, we will actually have to call head.next value, and we will have to call our recursive copy random list method again. So let's do that. In same way, for the random pointer, we will also have to do the same thing. Basically, once this has been completed, we simply need to return the node. Let's try to run this code. It seems like our solution is working as expected. Let's submit this code, and our solution runs pretty efficiently in time complexity compared to a lot of other solutions. In terms of space complexity, there can still be improvements made, but I guess you can figure that out. I'll be posting this solution in the comments, so you can check it out from there. Thank you.